I have trig functions, and to start off with trig functions, I want to talk about radians. And so radians can be a little bit confusing, but the textbook definition of a radian is a central angle has a measure of 1 radian if the radius of the circle equals the subtended arc. So what does that mean, really? Okay, it's easier to think about it if you look at it on a circle. So here's my circle, and here's the center. If I draw the radius of the circle and label it r, so here we have a line, and its measure length is r. Say we took this line here and wrapped it around the circumference of the circle so that this line also equaled r. So now we have these two equal segments. One is an arc and the other is the radius, but they are both equal. So this forms an angle right here, is a little angle. And this angle equals a radian, and a radian is approximately 57.2958 degrees. So now we've created a radian. And now we can start looking at the whole circle instead of just 1 radian. Here we have the unit circle, which will be used a lot during this unit. So we already talked about 1 radian, right? 1r, that's how it's written. So now let's talk about the whole circle. The circumference of an entire circle, of any circle, is 2 pi, and that's in radians. And that's labeled right here on this graph, or not graph, but circle. It says 2 pi. So the unit circle is split up into increments, like you see here, all on the inside here. And these increments are all labeled in radians. So now let's talk about the arc length of a circle. As you can see, I've written here S equals the arc length. So that's just what it's labeled as. And the S is given by S equals R times theta. And theta is the angle in radians, whereas R is the radius. Now we can begin an example. Okay, so I'm just going to draw a circle. This circle has a radius of 3, so R equals 3. And then it has a central angle of 2 pi over 3. So this isn't exactly drawn to scale, but we are going to find S, which is this arc length here, S. Okay, well, this doesn't look too hard. We just use our equation over here. S equals the radius, which is 3, times theta, which is the angle that we are given. And that is 2 pi over 3. Okay, well, we're dividing by 3 here and multiplying by 3 here. So it looks like those just cancel each other out. And S is left to equal 2 pi. So this measure right here equals 2 pi. So some people might be thinking, how is this related to trigonometry and trigonometric functions? So I chopped these two pictures out of the book, and it begins to relate the functions of trigonometry to a circle. As you can see, we have the 6 trigonometric functions right here. So on the left sides here are proportions that relate it to this circle. So this is saying that the measure of theta, right here, theta, when the measure of theta is placed in a standard position at the center of the circle with a radius r, right here, the 6 basic trigonometric functions of theta are defined as follows, and that's over here. So now we're going to use that information we just looked at to do an example. Here's the example. Let 4, 3 be on the terminal side of theta. Find the value of sine, cosine, and tangent. Now you can see I've drawn a picture to model this, and I also want to note that the coordinates for this is for -3. As you can see, I add in a little dash right before the 3. That was my mistake, so just take notice of that. So you can see that I've now drawn this triangle on a coordinate plane. So you go to the right 4 and down 3. As you can imagine, this triangle could be part of a circle, like this. Okay, so that's not the best circle, but it goes through the point 4, -3. What we're trying to find in this is the variable r because that's also the radius of the circle, as you can see, because this is the center of the circle. So let's just do our basic a squared plus b squared equals c squared Pythagorean theorem to solve for r. Okay, so now that I've done out the whole equation, we see that r equals 5. And we could have known that because it's a 3, 4, 5 triangle. This is a right triangle, as I now have denoted with that little box in the corner. So now that we have the information for the side lengths of the triangle, we can now determine the sine, cosine, and tangent. Of course, I'd like to point out that we're finding these sine, cosine, the trigonometric functions of the angle theta, which is always going to be this angle right here. So I quickly just redrew the circle that has the triangle inside of it with all of these side lengths labeled. Now you can see I have incorporated this little picture that has all the trigonometric functions in relation to how they are placed on a circle. So now it's really easy for us to determine all of the proportions, the trigonometric proportions of the angle theta. Now I've written out all of the trigonometric functions. Now you can just take a minute to see how the radius, the x-coordinate, and the y-coordinate relate to each of the trigonometric functions. Now we're going to move on to the basic graphing of trig functions. Let's start with the most basic of cosine functions. Y equals cosine of x. Okay, so it's not the easiest to graph points on an iPad, but here's what a basic cosine function looks like. As you can see, the point starts at 0, 1. It goes through pi over 2, and then goes down to pi, then up to 3 pi over 2, and then the end of one period is at 2 pi. So I just want to note that a period is like the duration of one full cycle of the graph. So let's just take a quick look at the domain and range of this graph. So clearly the domain, which is the x values, can go all the way from the far left to the far right. It can go from negative infinity to infinity. So that's what the domain is. So now the range is the y values. So you can see the range is a lot smaller than the domain. And you can see it goes from -1 to 1. And so that's the range, which will be in brackets because it touches -1 and it touches 1. So that's kind of hard to see there, but that would be the range for this basic cosine graph. Now let's move on to sine graphs. Once again, we're going to do the most basic sine graph, y equals sine of x. So now that I've plotted the points for the sine graph, you can see that it's very similar to a cosine graph, but there are some differences. As you can see, it starts at the point 0, 0, and then goes up, it starts up, and crosses over the point pi over 2 at 1, and then goes through pi, and then goes down to 3 pi over 2, and then begins back up. Once again, the period is 2 pi, so that's the duration of one full cycle of the graph. As you can see, the domain and the range are the same as the cosine graph, so we're not going to take too much time going over that. Here we have the graphing of the trig function y equals tan of x, the basic tangent function. Now that I've plotted the graphs, you can see they look quite different from the sine and cosine graphs. You can see in orange I've drawn asymptotes, and so each graph is kind of contained by these orange asymptotes. So the period of this function is a little bit different. It's only pi instead of 2 pi. As you can see, this box only has a range of pi. And by range, I really do mean domain. Talking about the real range, you can see that this graph can extend as high or as low as it wants. Now for the graphs of secant, cosecant, and cotangent, I decided to just take a picture of the book to demonstrate what the graphs look like instead of graphing each of them out because they're pretty similar, and once you get the hang of graphing these graphs and know what they look like, it's not that hard. So I'll just briefly talk about each graph. So first we have secant, and you can see these red lines here which I've now highlighted in yellow, are once again asymptotes, similar to the trig function we looked at. You can examine these closer and see what the domain and range are, which are highlighted right here. And once again, the period is 2 pi. So if you want to pause this video and take a look at the graph closer to see where it begins and ends, you can do so. Also, a good way to think about it is it's kind of the opposite of a cosine graph. You see, it doesn't go in between, it doesn't go in between the points of the range of 1 to -1 right here, whereas that's where a cosine graph is contained in a usual circumstance. Moving on to the cosecant graph, you can see that it's very similar with similar asymptotes, except they're at different places on the graph. Just like a sine graph is just kind of like a slightly moved over version of a cosine graph, the same goes with cosecant and secant graphs. So if you want to pause and check out the domain and range, the period's the same, but you can just take note of where this graph begins and where it ends. The cotangent is a little bit easier to look at because it's kind of like a reversed tangent graph. The period is the same, domain and range is similar, but if you want to pause that and take a look at it, whereas a tangent graph would usually go like this, the cotangent graph goes like this. So they're just kind of opposites of each other and they mirror each other. It's pretty easy to grasp. So we all know that graphs are not always in their most basic form. They're all often variations of each graph where they move left, right, stretch up or down, and whatever. So let's look at how they can move. Here I've got the complicated function y equals AF times b parentheses x plus c close parentheses plus d. Okay, so what does that mean? Let's start breaking it down. You might want to get out notes or something to write these down with as I explain. First, let's talk about A. A at the beginning here determines the vertical stretch or shrink of the graph, and it also tells if it's reflected about the x-axis. For instance, if A was negative, it would be the graph would be reflected about the x-axis. And also, if it is a small number, such as 1/3, the graph will flatten out. So just quickly demonstrated here, the black graph is just a normal sine graph, and the red line demonstrates what happens if you make the A 1/3. So you can see it just flattens out a little bit. It still grows through the points 0, 0, pi 0, and 2 pi 0, but you can see the x coordinates are just slightly smaller. Now the next part of the graph is f, and that's really easy. That's just the function, whether it's cosine, tangent, cosecant, whatever trig function it is. Next we have b, which is similar to a. It determines whether there's a horizontal stretch or shrink and a reflection about the y-axis. So you can picture what that looks like. If it's negative, it will have a reflection about the y-axis, and the horizontal stretch or shrink is similar to, if it was 1/3 or 3, whether it would shrink or stretch. Next is x, which is just the variable in any graph, so we can move right on to c. So c is a horizontal shift, so I can demonstrate that right here on the graph. Say c was pi. So the green graph shows how I just moved over the graph by pi. That one's not too difficult. And the same goes with our last variable, which is d. D moves the graph up or down. So if it's +1 at the end, +1 equal plus d, then the graph actually moves down 1. If it's -1, so minus d, the graph actually moves up. So it's the opposite of what you might think. But once you have that ingrained in your head, it's not that hard. Let me demonstrate. So I've shown this graph in yellow, and I put +2 over here just so we remember that even though it says plus, we're moving the graph down. So we're moving the graph down 1, 2. So this point right here goes down 1, 2. And you can see all the other points just do the same. So that's not that hard. We're just moving the graph around the grid. So now I would demonstrate the other graphs, the cosecant, secant, and whatever, and how they move, but it's all pretty much the same thing, and once you know the variables and how they move, you can pretty much do any graph. Really, practice just makes perfect.